In this lesson, we will be using the integral test in order to determine whether or not an infinite series converges or diverges. We will also be figuring out whether we have convergence or divergence for a p-series and a harmonic series. If you remember, we did discuss harmonic series very briefly in 9.2. So first, let's get into what the integral test tells us. The integral test tells us that if we have a function that meets the following criteria, it is positive, it is continuous, and it is decreasing for all x values that are greater than or equal to 1, and we let the function be the same as our sequence inside of the series, the theorem concludes they either both converge or they both diverge. So basically what the integral test tells us is that if you're given an infinite series and you're trying to figure out, does this converge? Does this diverge? I'm not sure. It says, oh, you can convert the problem into figuring out whether or not this improper integral, which we studied in section 8.8, does that converge or does that diverge? So let's see an example of how to use the integral test. So in example 1, I'm trying to figure out whether or not this series converges or diverges. I want to take a second and give you some perspective in this course. We're going to be looking at several series and determining convergence or divergence. In the previous lesson, we learned about the nth term test for divergence. So let's say, and basically what I'm trying to get to here is when you take the final exam, it's not going to say use the integral test. It's just going to say determine convergence or divergence. In this video, I know I'm going to use the integral test because that's what we're learning in this lesson. But to keep things in perspective for the entire course, if I started this problem and I were trying to figure out convergence or divergence, I would start with the nth term test for divergence, which tells me to start the problem and take the limit as n approaches infinity of the sequence on the inside. This is how 9.2 ended. When I take that limit, I get 0. What does that tell me from the previous lesson? It tells me that I can't use the nth term test for divergence. Remember from section 9.2, the nth term test for divergence only applies if the limit is not 0. Our limit is 0. So that test does not help me. So now I'm going to move on and try to apply the integral test. Let's see if we even can apply the integral test. In this case, I look at my a sub n, and I see that it is n divided by n squared plus 1. So I conveniently choose my function f of x to be x divided by x squared plus 1. That is something that is easy to integrate. That's one indication that I might want to try the integral test, because I do know how to integrate that. I could do that with u sub. Before I even try to use the integral test, let's see if it applies. Is this function positive when x is greater than or equal to 1? It is. F of x equal to x divided by x squared plus 1. If I'm plugging in numbers that are 1 or more, this is greater than or equal to 0. So I've shown the first condition of the integral test. Is this continuous? It is. This function has no discontinuities, no vertical asymptotes, and no holes. That denominator never equals 0. And is it decreasing? Is the function decreasing? Hopefully that question reminds you of Calculus 1. We determined when functions were decreasing using the first derivative test. We do need to pull that back out and apply it here. So we need to calculate f prime, find critical values, and see if this function is decreasing. I'm not working through the details of it, but take a second and use the quotient rule to find f prime. You should get that f prime is equal to negative x squared plus 1 divided by x squared plus 1 all squared, which has critical values at negative 1 and 1. And when we test those critical values, we should all be able to conclude that the function is decreasing on the interval from 1 to infinity. So I do know that the function is decreasing. And yes, all of this needs to be shown. You cannot apply the integral test if you do not show that the function is decreasing. So all of that work just to conclude that we can use the integral test. So we need to evaluate the integral from 1 to infinity of x divided by x squared plus 1 dx. Whatever this integral does, the series also does. This is an improper integral. We evaluate it by introducing a limit. I replace the infinity with b, and I'm going to let b run to infinity. I'm going to do a u sub. I'm going to let u be my denominator. Differentiate that. I don't have the 2 in my integral, but I do have an x dx. So I will divide both sides by 2 to see that 1/2 du is equal to x dx. Let's continue this u sub off to the side. So we're integrating 1/2 the integral of du over u, which is 1/2 natural log absolute value of u plus c. Absolute value is optional here because our u is always positive. So now let's actually go back to our integral now that we know what the integral is. We still have the limit. We just went off to the side here and we found that all of that integral is equal to this down here. So I have 1/2 natural log x squared plus 1 that I need to evaluate from 1 to b. So the limit is still in front. Let's start and plug in our upper limit of b. And then let's subtract and plug in our lower limit of 1. So we have the limit as b approaches infinity of, well, as b approaches infinity here, this goes to infinity. Natural log is an increasing function. It increases off to infinity. This entire expression, this entire limit goes off to infinity. So if this integral is equal to infinity, then the series must also be diverging because the integral diverges. So this diverges by, what test did we use? We used the integral test. Beginning with this series, if I were trying to determine convergence or divergence, I would always start with the nth term test for divergence because it's quick and it may give us a very fast answer. If we take this limit, we see that this limit is equal to 0, and so I can't use the nth term test. But I do notice that if I let my function f of x be 1 over x squared plus 1, one thing is that that is easy to integrate. So that is an indication that maybe I want to try the integral test. But in order to use the integral test, I have to check that there are some conditions that are met. First, when x is greater than or equal to 1, this function is positive, and it's also continuous. That function does not have any discontinuities. So I've taken care of 2 of the conditions. The next thing I need to show is that the function is decreasing. You need to take the time to calculate the first derivative of this function. You should get negative 2x over x squared plus 1 quantity squared. You could use the first derivative test, or you could point out that that's always negative. The numerator is always negative when x is greater than or equal to 1, and the denominator is always positive since it's squared. So I do know that the function is decreasing. If the derivative is negative, the function is decreasing. So all of this tells me that I can use the integral test. So now I will go to evaluate the integral from 1 to infinity of 1 over x squared plus 1 dx. This is an improper integral, so I will introduce a limit as b goes to infinity, and I'll replace my upper limit of infinity with b. This integral is equal to arctangent. That is an integral rule that we have. We will need to evaluate this arctangent from 1 to b. So we have arctan b minus arctan 1. As b goes to infinity, the graph of arctangent approaches pi over 2. And arctangent of 1 is pi over 4. And pi over 2 minus pi over 4 is equal to pi over 4. If you need a little bit of guidance with this limit here, the limit as b goes to infinity of arctan. I believe back in section 8.8, I reminded you of what the graph of arctan looks like. Graph of arctan is right here in blue. Hopefully you can see that as we're going to infinity, the function is approaching pi over 2. That's where that's coming from. And then to evaluate arctan of 1, I'm using Math 172, inverse trig. What angle between negative pi over 2 and pi over 2 has a tangent value of 1? That angle is pi over 4. That's where this comes from. Next, we have the definition of a p-series. And a p-series is a series that has the form of the sum n equals 1 to infinity of 1 over n to the p power. So that looks like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, so on and so forth. P is some positive constant. When p is 1, we've briefly seen that series before. We've discussed that. This is the harmonic series, 1 plus 1/2 plus 1/3 plus ... And we're interested in whether or not this series converges or diverges. It converges if p is greater than 1, and it diverges if p is less than 1. More specifically, if p is between 0 and 1, including 1. So the harmonic series that looks like 1 over n diverges. That is a p-series where p is equal to 1. The p-series with p equal to 2 is a sum of 1 over n squared. In that case, p is 2, which is greater than 1. So this converges by the p-test. This theorem here is the p-test. Rather, I'll call it the p-series test. In our next example, we want to determine if this series is convergent or divergent. I do have a small typo here. Please disregard that p. We just want this to be the sum from n equal 2 to infinity of 1 over n natural log of n. A couple of comments. This sum starts at 2. Don't let that confuse you. That's not that big of a deal. Remember that adding or subtracting a finite number of terms is not going to affect convergence or divergence. I would start with the nth term test. I would quickly take the limit as n approaches infinity of 1 over n natural log of n. The denominator is going to get larger and larger. That limit is 0, which tells me that I can't use the nth term test. It does not apply. I can only use the nth term test when this limit is not 0. So, thinking of what we know so far, if I let f of x be 1 over x natural log of x, I know that's easy to integrate. If I were asked to integrate that, I can quickly see that a u sub will work if I let u be natural log of x, because du is 1 over x. So let's check the other conditions for the integral test. It is worth noting that the function f of x is positive and continuous when x is greater than or equal to 1. The only place this function will have discontinuities is if x is less than 0. So this condition is satisfied. So it's okay if x is greater than or equal to 2, even better. We need to show that the function is decreasing. To do that, you need to find the derivative of this function. I'm not going to go through that, but you should be able to show me that f prime of x is negative 1 plus natural log x over x squared natural log x squared, and that is always less than 0. So the function is in fact decreasing. Now that we have shown all of that, now we can apply the integral test. So the integral test tells us to evaluate the integral from 2 to infinity of 1 over x natural log x dx. If it's helpful, you can rewrite this integral as 1 over x natural log x in the denominator, just to help you see when you do your u sub. I will introduce a limit. When I do the u substitution, we have the integral of du over u, which is natural log u plus c. And remember that our u was natural log. I chose that back here. So this is natural log of natural log x plus c. When I go back to my integral, I won't put those plus c's in there because we do have limits. So we'll apply the fundamental theorem of calculus and evaluate natural log of natural log x from 2 to b. We start off and evaluate it at the upper limit of b, giving us natural log of natural log b. And from that, we subtract natural log of 2. As b goes to infinity, natural log goes to infinity. So this entire first term goes to infinity. This limit's equal to infinity. We are then able to conclude that the integral diverges by the integral test.